Team Polar, a group of students from Eindhoven University of Technology, is developing an autonomous vehicle to make research at the South Pole more sustainable, affordable and efficient. TNO supports the team by sharing facilities and giving guidance from experts. In this episode, we dive into the mechanics of the Gen 2 rover. This autonomous vehicle weighs 300 kilograms, carries 6 square meters of solar panels and is designed to operate autonomously 24/7 in temperatures of minus 40 degrees. Designing an autonomous rover for polar conditions means making tough choices. Solar panels and batteries both play a crucial role, but each comes with limitations. For the Gen 2 rover, the challenge is not choosing one over the other, but finding the right balance. First tested in TNO's labs and then Gen 2 travelled to Sweden, where the team put both systems to the test. How do the solar panels and batteries perform? Let's start with the solar panels. Solar energy is clean and lightweight, but in extreme cold and low light conditions, performance is unpredictable. Snow cover, low sun angles and short daylight hours all affect how much power the rover can generate. Experts from TNO guide Team Polar. In Antarctica, you want to prevent snow from sticking onto the panels. And so previously, in the road to Antarctica, the student team tested the coated panels and uncoated glass solar panels in a skiing hall with snow machines to blow snow over the panels. Does the snow stick? And to which panels?
We're in the Uithof in The Hague and we are testing our solar panels. So what we've done is we made a number of coatings on our solar panels and we are testing to see how well the snow sticks to these panels. And so what we did is we had a bunch of snow cannons blowing the snow over and then we were observing what sticks and what doesn't.
This is a test panel with a glass and we coated this one. And then this is the uncoated, no glass, just the panels that we currently have on the vehicle. And then you can see that here there's not much snow and ice deposition, whereas here you have still patches of ice forming and then it sticks, and then as the snow accumulates it sticks onto the ice and it forms clumps, and these clumps hold on a lot more because they're a lot stickier.
Now it's time for the real deal. Time to test the solar panels in the cold.
But it's still sticking more on this side than it is comparatively on this side.
If you have the shell, you would expect the top part of it to be the most effective one, like the ones that are generating the most energy, but that is not the case. It's actually at an angle of more or less 70 degrees that it generates the most amount of energy, and this we got from solar yield models.
But what if the solar panels do not give enough power due to weather conditions? Batteries provide reliability and continuity, but they add weight and extreme cold can significantly reduce their capacity and lifespan. Luckily, the team was able to use the climate chamber at TNO in advance to test how they would perform before getting there.
This looks a lot like a microwave to me. Can you tell me what it is?
Yeah, so this is our climate chamber connected to a cycler. In here we connect cells and we subject them to different currents, voltages and temperatures. In here, currently for Team Polar, we're looking at the performance of the cells and we're trying to understand which is better at the lower temperature.
And that's exactly what you're doing for Team Polar, and I guess that means you're going to be using lots of low temperatures. What can you expect to happen with a battery at low temperatures?
So the batteries here at low temperatures will probably not be able to release all their energy that they would be able to release at higher temperatures.
There's other changes as well.
Yeah, indeed. So here we have sodium cells, these two cylindrical cells here, and lithium cells. So the lithium cells have the three predominant chemistries available now. So LTOs, NMCs, and LFPs. Each have their own performance benefits. For example, LTOs can charge very high currents at low temperatures. NMCs can pack a lot of energy per unit weight and per unit volume. And LFPs are typically cheaper.
Do you think it would be good to get Team Polar in and understand a bit more about the application?
For sure, maybe they can tell us about the temperatures that the batteries are subject to and the environment in general.
These climate chambers are a perfect way to test the Antarctic conditions because as we might go to the South Pole, we have minus 40 degrees Celsius temperatures, and of course these can simulate that.
So the rover's covered in solar panels, so why do you even need batteries?
You need a buffer to store this energy, and of course batteries are perfect for that, so that we can theoretically drive for an infinite amount of distance.
Brilliant, thanks very much.
Time to test the battery in the cold. How does the battery react once they're out in the ground in Sweden?
How have you prepared for coming to the cold? Have you had to do any modelling of cells, etc.? And what do you need to do still before you go to Antarctica?
So modeling of the thermal behavior of the cells was quite important. From that, we also got help from TNO with cell characterization, and our contact Alessio really also gave us some lectures and workshops on how batteries behave, especially lithium-ion batteries, which is quite useful since they're the biggest players right now.
And that's the final chemistry you're going to go with when you go to Antarctica as well, or is it still?
Yes. So the lithium-ion family, of course, diverges into many other chemistries. So this is a lithium iron phosphate, or LFP as it's commonly referred to. It is much heavier to the counterpart which we're going to be using. However, it does offer thermal stability.
So our mission by coming here is to test the mechanical design that we've been working for the last year and developing, building, spending multiple hours in the workshop to prove that this logistics can be done without kerosene and can be done in a sustainable way. That's why we hope that this trip proves that the mechanical design is valid, and it will enable us to traverse in Antarctica.
After years of design, months of preparation, and days travelling up here, for the first time Gen 2 rolls out into the snow. Finally it's time to see if everything performs as required. Everything is going well, and straight away the rover conquers an incline even steeper than what it was designed for.